forgot to record, and I forgot to invite Gabe to the meeting because he likes to be here. So give me just a sec. Just going to my email. Just a sec, Pete. Okay, so sorry for that. Okay. So yeah. So these people are here to help you. Please attend. The homework is due tomorrow at 9 p.m. So this is a great time to answer to get some of the harder questions answered. The last question on the homework, be careful with it because it's a bit tricky, right? You can get lost in dimensional analysis. But today we're going to do some more practice with dimensional analysis, and hopefully by the end of today, you will all feel confident. And so yeah, thanks everyone, first of all, for being here. Thursday is always sort of the most, today the stuff we cover is almost food for the soul, okay? The stuff we will talk about is going to be really interesting and relevant. And hopefully this is the sort of thing that will inspire some of you to continue studying some of this stuff. Yes, Lon. Okay, you're in the right place. Okay, so dimensional analysis continue. So to begin with, we sort of talked about different conversions, right? Like feet to inches, right? And seconds to hours, or hours to seconds, right? And we figured out that if you, for this example, if you multiply by 12, you can get from feet to inches, or if you multiply by 60, you can get from hours to minutes. I made the same mistake last time. So on and so forth. So there are certain conversion factors that are really useful. There's a different system of measurement, which is called the metric system. I'm sure you're all familiar with this from your science classes. What makes the metric system so beautiful and convenient is that the conversion factors are all very intuitive, and that the conversion factors are all powers of 10. In other words, they're all either 10 or some exponent of 10. So you can have, so this is not a 0. This is just like a thing where you put an exponent. So this can be any integer, right? So like 1, 2, 3. So in other words, you come out with this huge diversity of scales, and it's very easy to get from one scale to another. It's not like some arbitrary number like 12, right? Like 12 inches in a foot, or 60. These, to get from here to here, you just divide by 10. To get from here to here, you divide by 10. So on and so forth. Okay.
12 isn't that bad of a number.
12 is not that bad. Yes, you're right. But it's a bit strange, right? And if you read about the history of sort of these numbers, so I know for time, for example, for we have 12 hours in a day, and 60 seconds in a minute, and 60 minutes in an hour. That comes from the Babylonians. And the Babylonians knew that it takes roughly 360 days for the Earth to go around the sun. And so they made a little drawing like in the sand or whatever. I think they wrote in clay tablets in Babylon. So they said, okay, so here's the Earth today. And in roughly 360 days, we'll be back in the same place. And so they said, okay, well, each day, that means that Earth travels 1/360th around this circle, right? And they defined 1/360th around the circle to be 1 degree. So that's where degrees come from. And so therefore, if you go all the way around the circle, you have 360 degrees. And if you go halfway around the circle, it's not half. If you go halfway around the circle, you have 180 degrees. And so you might be familiar with counting in 60s and all that. Okay, so Danielle, I will explain what I've written. But anyway, so what I'm saying is that a lot of our units come from sort of ancient tradition, and the metric system sort of does away with this arbitrariness. For example, the foot, it's literally like, it's actually, I think most people's feet are shorter than a foot, but it's based on the size of a human foot, which is just strange, right? It's not as universal as maybe we would want, right? So this is a beautiful system, and it does away with these somewhat arbitrary numbers. The reason we like 10, it's not that 10 is like particularly special, but our counting system goes in tens, right? We have a decimal system. So that's sort of, we have 10, that's because we have 10 fingers, right, and 10 toes. So, so you can reduce a lot of math, at least counting systems, to sort of human nature, right, and culture. But this is a nice way, because multiplying by 10 is easy, right, in a base 10 system. So people have already started writing. King Henry died drinking chocolate milk. Thanks, Daniela. Thanks, Leanne. Thanks for everyone who wrote that in the chat. That is the way I learned this in 5th grade. My 5th grade math teacher told this to me. So the way to remember these, which you definitely need to know for the SAT, one way is, you can look in the chat, but King Henry died unusually is how I usually, that's what I was taught to remember that there's another unit here. Or you could just think of units, right? But yeah, for the sake of the mnemonic, unusually, yeah, drinking chocolate milk. Okay, sorry for the bad handwriting. There's no math in this. This is just a way for you to remember, right? What do these things mean? So first of all, these are just prefixes, right? These letters by themselves don't have any physical meaning. These are just numbers that you multiply a unit by. And for the sake of our discussion, we'll be using the unit of distance for most of this lecture. But you can obviously have, kiloseconds, that would be 1,000 seconds, or you can have, decaseconds or deciseconds. So you can do this with time, you can do this with weight. You can use kilograms. I'm sure you've all heard kilograms, milligrams, so on and so forth. But for the sake of this lecture, we're gonna stick with length. But note that these can be applied to any type of unit, which is another great power of the metric system. And so this is the basic. This is sort of where we all start with our units, right? And this is the U signifies exactly that, units, and it refers to your unit multiplied by 10 to the 0. And what is 10 to the 0? Anyone?
0.
No, 10 to the 0 is not 0.
1.
It's 1.
1.
It's 1. And if you're confused as to why 10 to the 0 is 1, you're going to see a pattern here as we build the system out, okay? Yes, Adi, you've said, while going under the base unit, does it go? That's right, that's right. And so we're going to go up first and then down, okay? So deca, if this is 10 to the 0, what do you think deca means?
10 to the first.
Say that again?
10 to the first.
Yes. And 10 to the first is what?
10.
Yes. So this is hecto.
10 in the second.
Yes. Now is that Adi? I think I can.
Sorry.
Okay, someone besides Adi, tell me what kilo is. Adi, I enjoy your participation, but I want other people to also.
10 to the 3rd.
10 to the 3rd.
Yes. And what is that?
1,000.
Yes. Very good. And now let's go down. So what is deci?
10 to the negative 1.
Yeah, look at the pattern, right? So here we're going up by 1 in terms of the exponent, right? And so now we need to go, so here we should also go up by 1, but that going from here to here, that would be going down by 1. So this should be a negative 1. And what is 10 to the negative 1?
0.1.
1/10, yeah. So I'm gonna, we can do that. Sure, 1/10. You could also write this as 0.1, whatever. What is this? What's the associated number, the factor here? 10 to the 1, 10, yes, 10 to the minus 2, which is, feel free to just say it so I don't have to check this chat. Yes. Okay, how about milli? What is the number?
10 to the negative 3.
Very good. Yeah, okay, now, so definitely know these for the SAT. By the way, I hope everyone is writing all of this down because you might need to know this for the quiz today, okay? Know this for the SAT. But for life, I think you all should know some additional prefixes that go above, okay, what you need to know for the SAT. So if you're sort of already overwhelmed, don't worry about this. But if you're interested, this is for you. Okay, so does anyone know what this is? The capital M?
Meter.
No.
Like meter.
Mega.
Mega.
Okay, so first of all, none of these letters have any physical meaning, right? These are just numbers. These are just factors you multiply your units by. So it can't be meters. Yes, so Steve the prognosis said mega. And does anyone know what mega? So we're going to break the pattern here. Here we're going up by 1 in the exponent. We're going to break the pattern. Does anyone know what the exponent is?
10 to the 4th.
Yes. 10 to the 4th?
Are you awake, buddy?
Sorry, 10 to the, what is it, 10 to the 6th, I think?
Yeah, 10 to the, and so Nishan, yeah, Nishan also had it right. So by the way,
I'm going.
okay, someone has your mic. Can you turn that off? Whoever's making a lot of noise back there. It went away. So, okay, thanks. I'm sure you did. Okay, so 10 to the 6th, and this is a million. And so I'm going to get to the point where I can't keep writing these numbers because they're going to get too big. How about the G?
Giga.
Giga, very good. And what is the corresponding number? The factor?
10 to the power of 12.
No, but that's a good guess.
Isn't it to the 7th?
Oh, 10 to the power of 9.
It's 10 to the power of 9. Yeah, and it refers to what number? Colloquially known as 1 billion.
1 billion.
So yeah, Nishan seems to understand what's going on. This is, I mean, we talk about gigabytes all the time in our computer world. We also talk about megabytes and kilobytes. These are vast numbers to store things, bits of not bits actually, things called bytes. And if you study computer science, you'll learn sort of what this is. Okay. Yeah. So I'm not sure. So there's a thing called terabytes, and that's actually the name of this next unit. And so some people have hard drives, like a 1 terabyte hard drive. That's a good hard drive to have, right? I don't know what the.
It is.
Yeah, I don't know what the what they use for bytes, like what the unit is for bytes. But anyway, I think it's just a B, right? Yeah, GB. Right? Anyway, yeah. So this is tera, and what is the number?
10 to the power of 12.
10 to the 15?
12.
10 to the 12, yes. And so this is what number? It's a trillion, right?
Oh, but can I see the pattern?
I wrote
where
the billion.
6, 9, 12.
Go ahead.
Like, can I see the pattern where it
See
goes?
the pattern. Good. So this is just the pattern we've chosen. They're intermediate ones, right? In fact, there are 2 intermediate ones in between each of these. But yeah, for our convenience, and most people will also just use these big 3, okay? Yeah, and note that I forgot 3 zeros when I wrote giga. This is the number 1 billion. This is million. This is billion, and this tera is a trillion. Okay, so 12 zeros. Wait, I need, okay, 3 more here. Okay. Okay, now let's go the opposite way. And there are fewer here, I think. No, there are more. Okay, we'll go faster. This is micro, and this is the Greek letter mu, and it's given by this symbol. And so those of you who have taken physics in high school will know, you might remember that the coefficient of friction, of static or kinetic friction, is given by mu. Okay, so that's what that letter is, mu. Here it refers to micro, which is 10 to the minus 6. Okay, nano, can anyone guess what nano refers to?
10 to the negative 9.
7.
9. Yeah, now we're going by 3s. And so first of all, micro is known as a millionth.
Nano is a billionth.
Billionth. And notice the TH, right? You have to be very careful when you say these things, because here you have million up here, million. Here we have millionth. Here you have billion, you have billionth, right? This is just the terminology. What is this little p? Does anyone know? Those of you who study sort of who are into science or chemistry would know this.
Pico?
Yeah, it's pico. Okay, so let me see. Let me read the chat because I've been neglecting that. Yeah, so people.
10 to the negative 12.
Very good.
10 to the power of 12, sorry. Negative
10 to the power of negative 12, yeah. And this is known as 1 trillionth. And what about this one? It's the highest we'll go.
12.
Femto, yeah. And there are cameras. Sorry, it's not spelled this way. It's fem. I always make this mistake.
Oh, I thought it was the locomotive.
And it's to the negative 15th. Okay. And there are you can find videos on YouTube of cameras that take video in femtoseconds. So you can see, so you can actually like resolve the motion of light, things that move really fast. It's really cool. I encourage you to go find some of those videos. Okay, so if you haven't written this down, please do write this down. And for the quiz, I might go back to this so you can see it during the quiz. Okay, I think it'll help people. Okay, so this is kind of just a long thing about the metric system, but very useful. Okay, so let's do a sample. Let's do a few sample problems. Let's convert a mile to kilometers. So I want you all to guide me through this.
Start with 1 mile.
Where do I go?
So on the bottom you put, so
Just remember.
if we're going in kilometers, you don't even need feet.
Well, okay, so there could be an immediate conversion here, but let's use the facts we know. And I think most people know this fact from 5th or 6th grade, right? And then we know that once we're in feet, okay, I'm just gonna do this. I'm just gonna do this first one. And then I want you to tell me the rest of the conversion factors. So this should say 5,280 feet in 1 mile. And now where do I go if I want to get 2 kilometers? What is our pathway? Feet to meter. That's one way to do it, but I don't know exactly how many feet there are in a meter, but what I do know is that there are 2.54 centimeters in an inch. Do you all know this? This was something I learned in 5th grade. You know this?
2.54 is equal to 1 inch.
2.54 centimeters, yep. So yes, so very good. So someone said feet to inch. So we need to go, so how many feet are there in an inch? Sorry, how many inches are there in a foot?
It's 12.
12.
Yeah, sorry, I'm tongue-tied here. Okay, and where to next?
2.554 centimeters over.
Go to centimeters.
Yeah, we need to go to centimeters, and then from centimeters we'll go to meters, and then we'll go to kilometers, right?
Yes.
Does the logic sort of make sense? So it's a long problem.
5 step.
Okay, now 2 meters. How many centimeters are there in a meter? This is
100.
100. Very good. This is using the information we just learned. And how many kilometers are there in a meter?
1 kilometer over.
Sorry. Yeah, other way. Yeah.
Is a
Go ahead.
meter.
Yep. 1,000. Okay, so someone with a calculator can. I'm going to rely on people using their calculators. Can someone do this and tell me what it is?
0.621 something.
0.621. And this is actually, yeah, if you look this up on Google, this is the conversion factor that's given, I'm pretty sure. So this is in kilometers. So if you were if you were in another
612.
612, thanks. Yeah. So this is great to know when you're traveling abroad, right, in countries that use kilometers, because you know that, yeah, if you're going like 10 kilometers, that's about 6 miles. Sorry, it's not 6 miles.
Kilometers isn't smaller.
Yeah, a kilometer is smaller than a mile.
Oh yeah.
Sorry. No.
No, a kilometer is Yeah.
half a kilometer, more than half a kilometer is a mile. So yeah, sorry, what I said was wrong. A kilometer is bigger than a mile. So you can travel fewer
A little bit.
kilometers. Yeah, sorry, I was confused there. So if I were to ask you how many miles are there in 10 kilometers, what would you do? No. You just use this fact, right?
Yeah.
So what would I multiply and divide by?
0.612 kilometers over 1 mile.
Is it that way or is it the other way?
Other way, sorry.
Yeah. So we need miles up here.
Miles.
And then kilometers down here. And yeah, 0.612. And so can someone do this for me? 10 divided by 0.612.
6.123.
I think you did 10 times.
0.21.
Yeah, I think you did. Whoever said 6.123, I think you did 10 times. Yeah, but it should be, say that again, Audie.
0.21.
Okay. Yeah. That can't be right. No, it should be, the answer should be more than,
0.6.12.
okay, that can't be, so this number, so we know that this number needs to be bigger than 10 because you're dividing by a number less than 1, right? So look, just do 10 divided by 0.612. Don't forget this point.
Didn't we do the dimensional analysis wrong?
Maybe someone did the factor wrong. Or did the calculation wrong.
Because 10 kilometers is 6 miles, around 6 miles.
Okay, so someone could have calculated this wrong, I have a feeling. But okay, so this is right? Everything here makes sense.
Yeah,
right.
that's correct.
This number, I don't know. I'm trusting on people's calculation skills, because I don't have a calculator with me. So
yeah, that is 0.612. 1 mile is 0.6123 kilometers.
Okay, so this is right.
Yeah, okay, I don't know how that's happening.
Okay. Anyway, let's not get sidetracked with just calculation stuff. But everyone understands sort of the
it's
method, right?
0.3
You're getting 0.3
in kilometers.
Okay. Let's save this for after. Okay. What I want you to be able to do is this. See, because I don't have a calculator. That's the only reason I'm not finding what this number is. But if you did this calculation correct, you should get the correct answer. Okay. Sorry, it's unsatisfying. Okay. Does anyone have any questions about how we did this? This is the important part. This is what we're really learning. No. Okay. For the sake of time, I don't know if this is worth it. This is a really fun problem. Convert your age to seconds. So say you were born, I don't want to make people share with me their birthdays because that's kind of it's personal information.
April 10th.
Okay, but I need to know the year and all that stuff. So don't
2006. Oh, sorry.
It's okay. I mean, it's if you're willing to share. Okay, 2006. Is that right? Okay, whatever. Anyway, this is worth doing on your own. Okay, I'm not going to spend time on this. I think a lot of this, this can come out of personal interest if you want to know how old you are in seconds. So maybe do this for fun. And note that today, if you do this today, note that June 11th, which is today, is the 163rd day of the year. But big picture, how would we do this? Let's just think about the units. Let's not even use numbers. So you have your age in years. And how do I go from years to seconds? We want to get to seconds, right?
Years to days.
Yep. And so how many? Yeah. I guess we can do the conversion units or the numbers. So let's just do the units for now. But yeah, that's right. Years to days. And now to where?
Days to hours.
Okay, Larissa already. Some people have already found. Wow, that's impressive. Some people have already found. Okay. Yes, days to hours. And now where?
Hours to minutes.
Yep. And now where?
minutes to seconds.
Very good. And that will give you, and so now you can fill out these conversion factors. I'm thinking, yeah, this is actually a more sophisticated problem, because if you really want to know your age in seconds, you wouldn't use, okay, we'll talk about the fine details, but let's just get these factors in so you can do it on your own. So I would use 365.24 or 25 days in a year. Does anyone know why we have this 0.25 business?
Because of leap year.
Yeah, very good. I'm so proud of you for knowing that. Yeah. The Earth takes a little bit more than a day to go around the sun every year. So it's not a perfect, like, the ratio between the day to the year is not exactly 365. It's actually close to 365.24. And so every 4 years, we account for that by adding a day to the year. Okay. Very good. I'm very proud of you. What about this unit? How many hours are there in a day? This is easy.
24.
Yep.
Yeah.
And what about this one? This is also easy.
160 minutes.
Yep. And what about this one? Same thing, right?
61.
Yep. Okay. So if you just, say you were, I don't know, 15 years old and you just put in 15 and you did this, that's not really right, because you haven't accounted for
Amount of leap years.
No, you actually have accounted for the leap years in this, but you haven't accounted for.
But all 4 of them? Like, you say you're 15, that means you've encountered 3 of them.
Yeah. So what this does, the power of this number, is it takes an average number of days in a year. This is the average number of days in a year. So it takes all the eccentric leap years and it factors them into, so to speak, factors them into this conversion. So you don't have to think about that. That's the point of this. Yeah. But what you are missing out on, does anyone know? So someone said they were born on April 10th. So that person, I don't know, could be 15, say.
The days you live like after your birthday?
Yeah. So we had April 10th, 2020 to today's June 11th, 2020. And sorry, not 2000. It's a long time ago. There has been, I don't know, 60 days. I don't know. You have to count the number of days between this. And not only that, you have to count, if you really want to know the right answer, you have to count the number of hours that we're into June 11th. So right now we're 10 hours in and 32 minutes in, and maybe even the number of seconds we're into this day. So you see how sophisticated this problem can be. My birthday was every day 6 seconds. Okay, anyway, so this is do you see the big picture, right? So it's a fun problem. You can actually, if you know some coding, you can even code your own birth, age in seconds sort of calculator. Okay, let's do a more physics.
Oh,
What is that, Adi?
I was saying something different.
Okay, here's a great problem. Convert the age of the universe to seconds. This is kind of a beautiful problem because if you get into this, if you study physics and you study that, this is a field of called cosmology, and it studies sort of the evolution of the universe. And if you, yeah, Leanne, yeah, it's beautiful. This is truly a highlight of the lecture today. So this field of cosmology, a lot of people will get onto their computers, a lot of researchers, okay? And they'll get onto their computers, this is your laptop, right? And they put in a code to simulate, they say, okay, the universe started here and there was this big bang, and they use what's called SI units. And this is the unit system that uses meters and seconds and kilograms and so on and so forth, right? All these familiar units, right? It's all metric system, and this is newtons and so on and so forth. They need, if they want to simulate the entire universe and its entire evolution up till today, they would need the age of the universe in seconds. And so that's why this entire problem becomes relevant. And cosmologists know this number off the top of their heads. So we're going to find out what this number is. And I want to have a little diversion, okay, just to entertain you all. How do people know? This is not math, not on the SAT. This is for you. how do people know the age of the universe?
They can use like mass. They can use like mass calculation tools and stuff like that, like computational, like satellite and stuff like that.
Yeah, so you're, in a sense, I mean, you're saying that technology sort of saves us.
Sort of. I mean,
what-
people like Plato were able to do that like without like the use of technology.
So Plato did not know what the age of the universe was. He made some.
Well, yeah, but like he was able to like figure like most of like the things in the world out without like any technology or any kind of like helping use.
I would hesitate to say this, okay? And I don't want to get too diverted, but religion, dating, nice. Yeah. Yeah. Okay. So Plato did not know that there were other galaxies in the universe. They thought that the entire universe was made of the Milky Way. So they had a very limited understanding, even though their understanding was deep and they knew a lot. But anyway, there was this guy named Hubble in the early 20th century who looked at galaxies, and he noticed that the farther he looked, the faster they appeared to be moving away from Earth. And that's exactly what this
radial velocities.
Yeah, exactly. Yeah. So there's a big thing. So anyway, you don't need to understand this really. This is just yeah. So the Hubble Telescope is named after Edwin Hubble, but he didn't use it. Okay. He was an earlier astronomer, but he made this beautiful discovery, and he plotted the distance. Look, this is distance of these galaxies very far away, right? The farther you go on this axis, the farther away the galaxy. And he plotted that versus the speed at which, okay, so people on the chat, let's focus, okay? So don't write anything unless you really need it. On this axis, what did he plotted the speed at which those things were moving away from Earth. This is called the recession speed. And this is, look, it's just a speed, distance over time, right? That's like a speed, right? And you can verify that. Then look, see how all these plots, all these points sort of align onto this line. So he plotted this line. It was like a line of best fit. And some of you who might be taking statistics or whatever will learn how to compute this line of best fit. Okay. And then he said, look, we've been talking about this, mx plus b, this entire course, right? Sorry, b didn't get in. What is m? M is the slope. And what is, he said, Edwin Hubble said that the slope of this line, he defined it to be this thing called h naught, or the Hubble constant. Hubble constant. And it turns out that the inverse of the Hubble constant is the age of the universe. And so I would like to verify, it's a very quick calculation, that look, the inverse of the Hubble constant gives you the right dimensions. And indeed, what is the slope given by? So the dimensions of the slope would be rise over run, and you can take rise over run of these dimensions, and you would get megaparsecs, which is the unit of distance, per seconds, over, so that's your rise. And what's your run? Megaparsecs. And what happens here? What cancels out?
Megaparsec.
The megaparsecs.
Megaparsecs, yeah. It is crazy. Thanks for the enthusiasm. So what is left? So you would have 1 over seconds over 1. And what is this? What is this reduced to?
1/5.
What is that?
1/5.
1 over second.
1 over seconds. So this is what h is in. So what is the units of 1 over h? It's just 1 over this, right? And what is 1 over this?
Seconds.
Yep. So indeed, so this is where the power dimensional analysis is truly handy, because you can sort of understand the physics of a dimension or of a value, like the slope of this graph. So indeed, the units of this, of the inverse of this slope gives you seconds. And it turns out that number, which is highly contested and people are still looking for an accurate number, that gives you the age of the universe. So anyway, that's how we know what the age of the universe is. That's one, and now there are many methods. This is the earliest method to find the age of the universe. Now there are many other ways to do it. But anyway, let's convert the age. So this is the value given in billions of years. Let's convert this to seconds. We sort of did something similar earlier. Let's do this together. What's the first step?
Year.
Years. Or actually, we can start with anything.
And you can't start with that. So first of all, I would write,
As long as it's
I would write this as its full sort of number. So 13.799 times, what is billion? Times 10 to the what? This should be either
10 to the 9th.
10 to the 9th. Yep. And this is years. And now we need to get to seconds. So now we need to go through this entire thing again. So years to days, right? What's next? Days to what?
Days to minute. No, sorry, hours.
Yep. Hours to what?
Minutes.
Yep. And what? Last.
Seconds.
Seconds.
And so we can fill out these conversions, and I'll do this for you. 365.24, 124, 61, 61, right? So can someone do this for me? Make sure you do it right, please. Don't screw up. Does anyone have it? Hello? Any luck? Anywhere?
2.6127084 times 10 to the power of 19. Big number. Good.
It's this.
Let's see what you people.
Yeah, Matthew put it as well.
Okay, so 4 point. Okay, can someone do this? So I don't know if that's right. Can someone do this? Pi to the 60th power in your calculator?
Like 6.75
Times 10 to the what?
times 10 to the
29th, I think.
Oh gosh. Okay.
29.
Oof. Okay. Well, that was not good. Someone once told me that the age of the universe in seconds is roughly pi to the 60th. That's what one of the.
That's not even close.
It's not even close. So I could be confusing things. But anyway, forget this then. But you found, and I trust some of your answers. 4.5 times 10 to the 17. It looks like multiple people got that. 4.35 times 10 to the 17. That's, yeah, roughly the age of the universe in seconds. So this is what you would, if you were a cosmologist, this is what you'd put into your computer, right, and chug, right? Great. Kind of cool, right? The age of the universe in seconds. Yeah?
Yeah.
Okay, great. We're going to talk a lot more about this thing called radians when we talk about geometry and trigonometry in this course, which is in a few weeks. So I'm going to forego this question for the sake of time, and I don't want to confuse people. But this is basic. There's no trigonometry in this. I've given you the conversion factor that there are 180 degrees in pi radians, and I've asked you to convert 10 degrees to radians. So you would just multiply 10 by
pi over 180.
Yeah, and that would give you the answer. Okay, we're gonna skip that, and we're gonna do one more physicsy thing before your quiz. The speed of light. Okay, so first of all, I mean, can things go faster than the speed of light? No, and sort of you say this.
Well, there is the speed of darkness, but that's sometimes.
I don't know much about that, but Einstein, who I think is a good enough resource for us, said that nothing can travel faster than the speed of light, and he made a beautiful argument. He said that the laws of physics are the same in any frame of reference, and the speed of light is the same in any frame of reference. And out of this came this entire field of relativity. but one of the sort of the driving force behind that was that the speed of light is given by a theory of electromagnetism. And that theory says that the speed of light is 1 over the square root of this thing, epsilon naught, times mu naught. So these are Greek letters. Don't let them scare you. This thing is just called permittivity of free space, and this is called the permeability of free space. And these are fundamental constants of nature. And I want to verify with you that, similar to how 1 over the Hubble constant gave us something in seconds, right? Gave us a dimension of seconds. I want to verify with you that this thing should give us a dimension of speed. And what is the dimension of speed in SI?
Meters per second.
Very good. So let's verify that this thing gives you dimensions of speed. And so I've said here, the dimensions of epsilon naught, the permittivity of free space, is this thing. You don't have to know what this is, but amps squared times seconds to the 4th over kilograms meters cubed. It looks horrible, right? And the dimensions of the permeability of free space is this horrible thing: kilograms times meters squared divided by seconds squared, amps squared. So they look horrible, but I want to verify that the dimensions of 1 over the square root of this times this gives you meters per second. Yeah? Seem doable? Yeah, you are getting a quiz. Okay. Okay, so let's do it. So let's just multiply the product. Actually, let's just do it all at once. So it's sort of big picture all at once. 1 over, I want to assess the dimensions of this, right? And so I'm going to put these dimensions in, right? So 1 over, okay, here we go. Ready? Amps squared, seconds to the 4th, kilograms, meters cubed, times, I'm just copying, right? That one, and now this one. Kilogram, meter, seconds squared, amps squared. Now, how do we simplify this? What cancels? You tell me. This is the part that you should know.
Oh, the K, G, M, one of them cancels, and then.
So the KG cancels, first of all.
Yeah.
Does anything else cancel completely?
The A2, I guess.
Yeah, don't say A2, say A squared. These are
A squared.
So those are gone. So let's just write what we have left. Seconds to the 4th, meters cubed. Oops, sorry, parentheses are bad.
Times second squared.
Times meter, don't forget the meters. Second squared. Okay, now can someone else besides Audie tell me what to make of this?
And so S squared and 1 of the meters.
Say that again.
And so S second squared and then 1 of the meters.
Yeah, very good. And so I'll do this slowly. The meters, I'm not sure about what you said, but
S squared over meter.
yeah, so I'm going to do this slowly. So I'm going to rewrite this entire denominator here as I'm just going to move this seconds under here and this meters here. And the reason I can rearrange that is because these are all in a multiplicative relationship, right? And you have things commute, right? You have commutative property, okay? And S to the 4th over S squared. There was a lot of this on your first homework assignment. What is that?
S squared.
Yep, that's S squared. And if you don't understand why, you can say S times S times S times S is S to the 4th. S squared is S times S. And look, 2 of those cancel. So indeed, S squared. And what is this?
M to the second?
It's not M to the second, it's 1.
Wouldn't it just be 0?
1 over
The
n.
top canceled. No, never mind, it's
It would
1.
be really bad if this were 0, because then you'd have 1 over the square.
Yeah. So 1 over.
M squared.
Yeah. Yeah, right? Because you could write this, we'll get to sort of exponent properties later, but you could write this as this, and 1 of the m's cancel, and so you're left with m times m, and what is m times m? 1 over m times m, and that's just that, right? Yeah? And now, what is this? The square root of seconds over, what is this? What is the square, first of all, what is that?
It's just A. So
S.
this will just be just S over M.
But yeah, it's actually the absolute value of A, but for the sake of units, it's just A. And in fact, remember, this was the definition of absolute value. But yeah, here it's And what is that? What is 1 over a fraction? Like what? If I had this, what is that equal to?
A.
A.
So what is this?
M over
M
S.
over S.
Hey. Isn't that what we wanted? We wanted our answer to be in meters per second, right? And indeed, we have shown that this thing is in meters per second. And when James Clerk Maxwell was a great physicist. When Maxwell found this, when he realized this, what we just showed, he was so ecstatic because he had just shown that the solutions to something that he had found called the Maxwell equations gives you a wave that travels at the speed of light. And he had thereby shown that light is an electromagnetic wave. So very profound, and we've just used dimensional analysis to, in some sense, verify his result. Cool enough? Someone say yes, please. Thanks. Okay, I'm going to send the quiz, and the quiz necessitates you watching a video. That's why I've given you 10 minutes. Notice I stopped at 10:50. The video, I'm going to share it in the chat. Some of you might have seen the video. Even if you've seen the video, you might want to watch it again because, let's see here. Because you'll sort of need some of the info. Okay, so I'm sending the video. It's the powers of 10 video. So it might be familiar to some of you, but do watch it, even if you've seen it before. And then in about 10 minutes, because that's 10 minutes long. So everyone turn off your microphone, watch the video, and in 10 minutes, at 11, I'll send out the quiz, okay?